Hello, this is Bernie Lewin from the Platonic Academy of Melbourne. It's autumn 2025, and my students asked me if I could record, um, or rather give them copies of the slides that I showed last week, which cover a few aspects of our geometry and how it relates to Pythagorean mathematics and so on. And so instead of giving the slides, I thought I'd just talk through them because they've actually got a bit of animation on them, so that doesn't really work. So this is a bit of a rough run through the slides. It'd be nice with this sort of thing to do a bit more of a classy video, but that will have to come at another time. So here we go. I'll just run through these slides. So it's Platonic esoteric geometry, part two. So we've done a little bit of this stuff in part one, and this is the more advanced class where we're looking especially at tessellations and at music. So this part is mostly about music, and I'll do something about tessellations in another video. Okay, I'm just going to share the screen now. Okay, and I'll set that up. Okay, so we've just been looking at tessellation. Well, we were looking at working in the square, and then working in the hexagon, and soon we'll be looking at working in the pentagon in terms of making stars or polygons, or stars within a circle, and then moving out from that to actually using those designs for tessellations. But before we move into tessellations, it's good to notice especially the design of rose windows in cathedrals. And I hope that students now will start counting in the rose windows how many compartments there are, or how many lines, radiating lines there are from the centre. And you'll notice that some are in the square, so you will see dominant radial lines of 4, 8, 16, or 32, or so on up in that geometric series. Or you might see 6, 12, 24, and so on. Or you might see in fives in the pentagon, where you would get 5 and then 10 and then 20 and so on. Sometimes, especially the square and the hexagon, those designs can be mixed together, so long as the factors work with each other. But what I'm showing here is the some uh, rose windows that are in the square. So they've got a dominant, perhaps 8, 4, and 8 compartments or lines. Okay. Now, we started getting on to music last week, and in the Platonic Academy, we discuss music in various courses, the harmony in music, and the Pythagoreans and Platonic work with that in terms of their geometry, in terms of the importance of ratio, of relation, of ratio, geometric ratio for music. And we introduced it in, so we do this in the Timaeus course, we do it in Geometry Part 1, and one other course I can't remember. So anyway, we can come to it in part two, as we did in the class, by looking at the sacred tetractys. So we've already looked in part one at the sacred and secret hex hexi sorry, pentagon and pentagram, the five-pointed star, and the importance of the golden ratio in that. But another very important secret symbol was the tetractys. So I'm going to introduce that here, and I'm going to introduce that in terms of figurate numbers or figured numbers, depending on it's two different terms. I think figurate now is the more modern term for these number series. So if we just, and how they relate to what's called the gnomon or the gomon, which is the sundial, the rod in the sundial, which is supposed to be the first scientific instrument in terms of the mythology that the first philosopher in the Greek tradition, Thales, brought from Egypt, because they celebrate the Egyptian science, and all great wisdom came from Egypt. And Thales comes back with the rod, the gnomon, sticks it in the ground and shows folks how he can tell the time with it. So the gnomon's also used in figurate numbers, as we shall see. Okay. So firstly, there's the linear numbers. You just put one pebble down. They talk about it in terms of pebbles. And then after that, in a line, you put another pebble and another pebble. And if you add them together, you get the 1, 2, 3, just the basic arithmetic series. Okay. But then you get the first plane number figurate series, which is the triangular numbers. And that starts again with 1, and then you add 2, and then you add 3, and then you add 4. And the way they thought about it, or the way they actually did it, we think, is that they would put a pebble in the sand, and then they would put their gnomon on the side, and then put 2 after that, and then put their gnomon down there again, and put 3, and put 4, and so on. Now, the gnomon is also the same name that's used for the set square, that the carpenter would use to get a perfect right angle. And one of the more important figurate numbers is the square numbers. So we go from the triangular numbers to the square numbers. So you put this right angle around the first pebble, and then 3 after that. You can see how that's kind of placed by 1 on each side and then 1 on the point, but it's a bit easier to see when you go further up, where you put the gnomon in here and the gnomon in here, and you get the square numbers. So it's not immediately obvious that 1 is a square number, but it's also a triangular number. It's everything. It's the monad origin of all, but 4 is perhaps the first square number, and then 9, and then 16, and so on. So they thought of it in this geometric, spatial sort of way. Okay, so the tetractys is the first 4 or 3, depending on how you want to think about it, the first, let's say, 4 stages of the triangular numbers. You go to that 4th stage and then you stop. That's enough, because there is so much summarized within this design, just up to the 4th. So that's the tetractys, and what we're going to do today is relate that to the their theory of harmony, in terms of mathematical ratios. Okay, so in part 1, we looked at the modes of standing waves when you vibrate a piece of string. Folks might remember that who did part one. We watched a video, and this is where you get a piece of string and you vibrate it at certain hertz, in certain vibrations per second, and at certain vibrations you get uniform waves. It gets messy, but then you get these standing waves. And in the video that we watched, the first standing wave came at 11 hertz. Just depends on the length of the string and the tension and so on. And then, so that was just, we're calling this here. I mean, it's so much easier for us to say this is one wavelength. Actually, it's half a wavelength, but forgive us here, we'll call that one wavelength, where you've got the string just moving up and down like that. And then you go to a higher frequency and you find at double that first frequency, for us it was 22 hertz, you get these two waves with one node in the middle in the string. And then you go up again, you go up arithmetically, you go to 33, and then you get three waves with the two nodes, and then go up again, 44, you get four waves, 55, you get five waves, and so on. So it's going up at these standard difference intervals, not a geometric ratio, not like doubling or tripling or something. It's going up in these standard intervals. And we can actually relate this to musical notes. So especially one way to relate them is that if you put your finger at this point and then pluck the string here, you will get what is an octave above. So an octave above, it means like when you start at C on the keyboard and you start at C on the keyboard, and then the next C up, the string is half the length. Okay, and then here, if you go to a third of the length, then you'll go up another 5 notes to the 5th note in that new octave. I think it's a G, something like that. And so basically, as we can see, it goes up very fast at first, and then it doesn't go up so much for each new mode as you're going through this is called the harmonic series. Okay, and here's a bit of a picture. You can imagine you've got your piece of string and you go to the halfway point and pluck this side, and you go to the third point and pluck this side. So these notes are all in harmony with each other, and this is the fundamental basis of harmony, is this harmonic series and these things in harmony with each other, these ratios, these notes, if you like, or tones. We should say tones, because the notes talks about the notation. Okay, but one of the reasons why we can see that they're in harmony is that, in fact, when you do pluck the string and get this note here, which we call the tonic, the main note, you also get sub-movement within. It's not a pure note. You get the shaking up and down like that, but you also get movement like this, and you also get movement like this, where the third, where you've got the 3 standing waves instead of the 1. So you've got the main one there, but within them you get these other little vibrations which you can actually analyze and your ear can hear. This is the main note, but these are the overtones. So it's hard to sort of picture them, and this is one picture of them where you get the fundamental note here, and it's showing this as the first overtone, which is also happening in there. It's not a pure note. I think the people who work with synthesizers call it a sine wave. When you hear the pure note without the overtones, it sounds not very warm at all. But these overtones give the note the warmth, and the mixture of the overtones, the intensity of each overtone, if you like, gives the timbre of the instrument so that you can actually tell, like a C on a guitar is different from a C on a piano or some woodwind instrument or something like that. So here in a spectral analysis of the wave, we can see that here's the main tone here, and here are the overtones going down in that harmonic series. And we'll notice that, like, it's not any consistent pattern here because this is a particular instrument. You can see you've got a cluster here and a cluster here, and some of these further down are more dominant than the ones further up this line, indicating what you can actually hear, I think. So you can see how different instruments give you a different spectrum each time, but it's all about this overtone mix. Okay, there's the fundamental first overtone, second, third, and fourth. So that's the half, the third, um, the quarter, and cutting it into fifth or 1/5. Okay, an interesting aside here. You can relate this to uh, natural design, where this is a X-ray of a shell, and it relates quite well to the harmonic series there. Okay, so back to the harmonic series of the piano. Now, like this is all very well. So, you think, okay, these are the notes that are all in harmony, right? This one here, this one here, this one here. And, maybe you can write a song about it, you know. Um, and or you can play it on an instrument, but this is a whole octave, and if you're singing, usually people can only sing, if they're lucky, within one octave. You can't sort of sing, you've already gone up to here, you've gone up 2 octaves. I mean, that, if people know their music, that's a big range. So the harmonic series, yeah, it's not very helpful for getting in the harmony of music or working out the harmony of music. The Pythagoreans and Platonists weren't the first to work out harmony. People just worked it out with their ears, going right back. Even Neanderthals had little flutes, right? We talked about that in part one. It's just that they worked out the mathematics of it, the ratios of it. But anyway, if you get all these notes, right, they're a long way apart, and they're a long way apart on the piano. Here are all the octaves here. And as far as the design of the piano goes, if you did actually design it with the same gauge wires or strings, then you would need a very long piano, because the ratio across the 7 octaves of a piano, C to C to C to C to C, or A to A to A to A, however you want to measure them, is 1 to 64. So if one string is 10 centimeters long, then the other string for the lower notes would have to be like 6 meters or something. So in fact, there was this teenager in New Zealand who recently designed a piano where I think all of the strings were of the same, or wires were of the same gauge. And it does have an amazing sound. You can see it on YouTube, but it's 6 meters long. So it was an engineering feat to get the frame holding all of those wires in this piano that's nearly 6 meters long. Okay, so here we go, the harmonic series, and we've just got these drawn in terms of lengths, right? And so we've got the first note here, or the where we're starting anyway, the tonic, or the first note. So that might be your C, and then that's your next C, and this is your next C here. In between, you've got this 1/3. Remember, we went from 1 wave to 2 waves to 3 waves to 4 waves. Well, this is how we get this series. Now, they're all in harmony. Okay. And so the first ratio, the ratio of the octave, is 1:2. And this is in the tetractys. Remember the sacred tetractys. This is the ratio of the first dot to the second dot. 1:2 or 2:1, depending which way you go. Now, if you go down to the next ratio here, this is 1/2 to 1/3. Now, this is a ratio of 2:3. Now, how can we imagine this? Well, just look at this here, and what you notice when you've got two ratios like this is you can say 1/3 is 2/3. 1/3 is 2/3 of 1/2. You can write that down or say it and see how it works, or you can work it out mathematically. What is the ratio of 1/3 to 1/2? Another way to look at it is to say, well, if I divide 1/3 in half, I get 1/6. And if you sort of look at 1/6 there, and there's another 6 there, there's also another 6 there. So there's 3/6 in 1/2, right? So those 2/6 is 2/3 of 1/2, if that makes sense. Or you double this and you get 1, and you double this and you get 2/3. However you want to understand it, this is a ratio of 2:3, and that's the second one in the tetractys. And here we've got here, the next ratio in the harmonic series is 1/3 to 1/4. 1/4 is 3/4, 3/4 of 1/3. Okay, and again, you can work that out however you like, but that's the way it is. That ratio is 3/4. So if you divide this into 3, right, you get 3/4 of 1/3. Okay, so that is the next one in the tetractys. That ratio of 3:4, or 3/4. So here we now have, right, now, well, what we can do now is we can open up the octave and we can put these ratios of 2:3 and 3:4 inside the octave. So we put this in by doubling the 1/3, because remember, and this is important, this is going up an octave. When you go from 1/3 and double it, remember, whenever you double or halve the length of a note, you go up an octave, and they're in harmony. That's the most important harmony, an octave. So you take this 1/3 and double it, and you've put it in between the tonic and the octave. So you found a note that a singer might be able to get to do harmony. And in fact, it is a very important note in all musical systems. And you can do the same with this one here. This ratio of 3:4, you can triple it. So you can go up 2 octaves, right? And you get this other note here, which is called the subdominant. So in musical theory, those people who don't know music, the dominant is very important, the dominant note, which is the 5th note in our system, but it's in almost universal. So in all different tonal music, the gamelan of Bali maybe is not a tonal music, but most music that's all about harmony will find the octave and will find the dominant, and perhaps divide the other notes, the other gaps, differently. But that's important. And the subdominant is not so universal, but important in our system. Okay, so you've got those by playing around with these ratios, by getting these ratios and plugging them into the octave. Okay, and we can see this now on strings and relate it to the tetractys. So we've got 1, 1/2, 2/3, and 3/4. Oh, hang on a sec. It should go the other way, shouldn't it? So here are our notes. You think of your length of string again. you put your finger there on the guitar or whatever, you put your finger there, you put your finger there, and you've got now in the octave, you've got four notes. You've got the first and the last and these two in between, and you can start playing around with them and making some very fundamental and very harmonic tunes. No challenging jazz is going to happen when you're playing around with that. Okay, so here we go again. We've got the octave 1:2. We've got 2:3 for the dominant, and we've got 3:4 for the subdominant. And that was one of the main secret things that the detractors was pointing out and symbolizing for the Pythagoreans. So the early Pythagoreans got this far. Did they get any further? We don't know, but we do know from Plato's Timaeus that he got further, and he presents how he got further and found what are the white keys on a piano. So the 7 or 8, 7 intervals that you get on the white keys of the piano, we find first in our tradition in the Timaeus, and then it influenced the future there. So the way he did that, I'm not going to go into this in a big way, but it's using what's now called the cycle of fifths, which is very important for musicians in terms of tuning, tuning string instruments, and also composition, finding harmony and dissonance as well, challenging it. So we've got going from one octave to another octave with those notes, and then what you do is you use the cycle, they say the cycle of fifth, is the 2/3 dominant is the fifth note, and what you do is get 2/3 of that. So you get the fifth note, and then you pretend that is your tonic, and then say, what's the fifth note for that? That's effectively in the mathematics 2/3 times 2/3. You go to that next note, that next fifth, and you take that as a tonic and say, well, what's the fifth note from there? That's 2/3 of 2/3 of 2/3. And you basically use that to find the other notes. So 2/3 of 2/3 gives you this second note here, which is 8/9. 2/3 of 2/3 of 2/3 gives you this note down here. You go up an octave to chuck it in here, and it's the sixth note. You go you get we've already got the fourth note. That's three quarters. Remember, that was the ratio between 1/3 and a quarter in the harmonic series. You can go back and have a look at that. So that's already there. That's really handy because it's harder to get that. But how do you get these other notes, these other white keys? Of course, they didn't have keyboards then, but we're just relating it to going backwards in time. How did they get the white keys on the keyboard? How did they find these 7 intervals, or as they call it, 8 notes, because they include the first and the last in their notes? Okay, so you get 2/3 of 2/3 of 2/3 of 2/3, 2/3 to the power of 4, and you bring it up from 2 octaves. You bring it up to 2 octaves, and you bring it up for double 2 octaves. That's right, and then you put it in there. And so what we've got here is the important pentatonic scale, which is important in music if you know your music. Okay, and so you get this final note here by bringing 2/3 to the fifth, and then coming up, bringing it up into the octave. Okay, so so that's when you get in these nice ratios, you get your white keys, you get notes that can be used for harmony on an instrument that perhaps doesn't have a big range, because they didn't have a big range in the old days, and the voice, of course. So the voice can play in harmony to the instrument, which the voice doesn't usually have a big range. Okay, so this is found in Plato's Timaeus. And we can have a look at this on the piano. So here's the visualization of the piano. And these are the ratios for each of the notes. And this was really important to Plato, that it used the ratio of 1:2 and 2:3. And that's all they needed, right? 1:2 for the octave, 2:3, and that cycle of fifths technique of getting all the other notes. 1:2, 2:3. It doesn't need 3:4. Okay. So if you like, C is the tonic here, and then you go to the fifth note, and then from the fifth note you consider that the tonic, and then go on and go on. That's the cycle of fifths. And we can visualize that on a circle, which is what we did in class. And this circle represents the semitones. So now we know that there's not, and they knew at the time there wasn't an even interval between all of these white keys there in the purple, the major notes, not the minor notes. So this is C sharp, this is E flat, and that's F sharp. So, but these are the major notes, and the intervals between them aren't the same. We know that now, and we can see that visually on the piano because there's not a black key between every white key, right? So, but anyway, if we draw this in a 12 semitone circle, we can see how you count around 7 each time to go down 1/3, or if you're counting the white keys, so purple here, you count the fifth, 1, 2, 3, 4, 5. You get to G, which is the fifth, and then from G you go 1, 2, 3. 1, 2, 3, 4, 5, and you get to D, and then you go around again. You go around this way, you get to A, and then you get to E, and then you get to B. Now, if you keep going around in the fifths, you start picking up the minor tones. And the Pythagoreans or Platonists later in the Hellenistic period picked these up using the cycle of fifths. And you can go around and find all the tones, right? Okay, but not exactly as we now have the equal temperament, which was worked out by Bach with his I've forgotten it now, his even-tempered clavier. I can't remember what it's called now. And from there, the mathematics was worked out that it's exactly the 12th square root of 2, which can be explained in Pythagorean terms, in Platonic terms, but we won't do that. But basically, if you go up by the 12th square root of 2, and then 2 times the 12th square root of 2, and 3 times the 12th square root of 2, and you keep going around until you get to 12 times the 12th square root of 2, which is 2. So you go right around through the octave from 1 to 2, if you like, through that doubling to get all of those notes. Now, if you compare that even temperament with the Pythagorean ratio stuff, whole number ratios that they used, it's not quite the same, and so it was slightly out of harmony, and this is something that on the string you could easily adjust for, but on a piano you couldn't. So it was a problem with claviers or pianos or harpsichords, and basically keyboards, piano accordions, and so on. And so that was a problem in going over a long range of octaves. So, and what you can see here is how they're not quite right. So those open circles show you where the Pythagorean ratios put you, and then the dark circles show you the even tempo. And you can see here, once you've gone around to every single note, all 12 notes, there is this gap here, which is called the Pythagorean comma, which was demolished once you got even temperament. Okay, and so this is the cycle of fifths, drawn in a slightly different way. We won't go into that. That John Coltrane used and discussed with a mathematician, became quite famous in that way because he showed basically how he was doing some pretty amazing mathematics in his composition. So that's John Coltrane. We've got a quote from Thelonious Monk: all musicians are subconsciously mathematicians, and also a very common, well-known quote from Goethe, which is music is liquid architecture, architecture is frozen music. Now, I was going to show this video giving the geometry of the cycle of fifths, but we will leave that for now, and maybe I'll show that in class. It's on YouTube. Okay, then I move on from there. Okay, here is Robert Flood's diagram from one of his books. So Robert Flood was like Elizabethan, so the English Renaissance thinker, Pythagorean Platonist. And there's this idea of the music of the spheres, and that the whole universe God has created in harmony. And this is his, I haven't got it written here, his monochord, divine monochord. So there's one string here, and that creates all harmony in the universe. So that's what we've been talking about it as in terms of one piece of string and dividing it into ratios. And we can relate this to not only mechanical waves in air, like vibrations of air, but also to electromagnetic radiation, where you get the colors and you get all sorts of other electromagnetic radiation, which is also very important in the science of particle physics. And in fact, as I've explained in other classes, when in particle physics now, if they talk about finding a new atom, a new boson or whatever subatomic particle, they're really talking about finding resonances. They send in radiation and see if they can get some resonances. So it is all about waves and wave ratios. And here's just an image giving the two-dimensional electrical and magnetic oscillation of the electromagnetic radiation. So it's different, but similar in terms of the mathematics to what's going on with sound. Okay, and so that's all for that part of the talk. For the moment, with that explanation of music. But you might find some other videos, and certainly in other classes, in the Timaeus class as well, and in part one, we talk more about music. But hopefully that guy gave you an idea without confusing things. So thanks very much for listening, and hope to see you in class soon. Platonic Academy of Melbourne, Bernie Lewin, Geometry, Part 2.